Okay, so so what do we want to do now? Well, that's the kind of big question. We're kind of not satisfied with this D because we would like to say more about what actually happens. So how to determine P, and thus also E, right? We agree that if I know P, then I can calculate E. Well, in order to do this, we need more info about the chunks of matter that we are dealing with. Yeah, so we need more info. And what's this info is what kind of matter are we dealing with? Okay, and here the discussion gets extremely elaborate. However, there's one case which makes it very, very simple again. So just a couple of minutes of gesticulation here. So what is P? P, polarization, density of dipole moments per unit volume. What can that be? Well, if I have like a simple gas or something, molecules that can be very simply elongated with the presence of the field, then things might be simple. I could imagine that in the absence of a field, that there is no polarization, first thing. I could imagine that if there is a field, then the chunk of matter will polarize along the field. Third assumption, I can imagine that irrespective of the direction in which I put the field, the chunk of matter will polarize in the same amplitude. Okay, so there's a notion of linear isotropic dielectrics. Tell you what these are, and then we'll talk about what things are. So linear, what does that mean? It means that P is proportional to E. Okay, and here I will write some absolute values here, because this is just to say that the size of the polarization is proportional to the size of the electric field that's applied to it. Okay, and here you see it's two things, right? So there's a statement that the size of the polarization goes with the size of the electric field, but there's a further statement that says that not only the size but also the direction goes with the direction of the field. Okay, and that's essentially, so linear isotropic means that polarization is proportional to E in size, but also in the direction of the field, irrespective of where this direction is. Okay, it absolutely does not have to be like that. So there are pieces of matter, they're called electrets, that have a permanent polarization to them. So they're like the electrostatic equivalents of permanent magnets. Okay, they're more rare, but they do exist. You could have a more complicated situation. So for example, if you have a molecule that has a certain structure to it, then this structure is absolutely not isotropic. And if the structure of the molecule is not isotropic, there's no chance that the response of that molecule to the presence of an external field can be isotropic. On the contrary, what's going to happen is that in your molecule, you'll have surpluses of positive and negative charge that represent some dipole moments in there. You apply some field, and your molecule will bend, it will deform. And you can compute these things with essentially quantum mechanical calculations. And it could be that if you apply a field in a certain way, the molecule deforms in such a way that the dipole moment is like that for a field like this. And then for a field like this, it becomes like this. Okay, that's all entirely possible. So you could have very complicated relationships. You could have P in general is equal to maybe some fixed polarization, P0. That's like structural. It never goes away. It's in there. And then you could have another kind of component here that depends on your direction of the electric field. And then there would be a certain like matrix here representing some susceptibility of the thing. So if you put a certain field in a certain direction, then this would give you a field in a certain basis direction, EI, with a certain thing. So you put a field in a certain direction, it polarizes a bit in another direction. And then you could have something which has a function of EJ, EK, and then triple, fourth, everything's possible here. Super complicated. Everything exists depending on the chunk of matter that you are. So the simplest cases are when you say this one in the absence of field is 0, these higher ones you forget about, and this one here is just diagonal. Okay? Most matter actually responds very weakly to such electric fields, and it's a very good approximation for most things to assume that they are linear isotropic dielectrics. Okay? So that's just the assumption we're going to make now. And now I go back to your wonderfully planted question. You see, in that case, it's completely done because we have now hidden the complexity in the detail of the actual relationship between P and E. So we're going to give that a name, okay? And that's where we come to the notion of the susceptibility. Okay, so for linear isotropic dielectrics, P is going to be some multiplicative factor of E. Okay, and this number is traditionally called chi E. Okay, chi E. So this is the electric susceptibility. So this susceptibility is like a laboratory accessible number. So you would take your rubber and you would measure the susceptibility for it. You could, if you were really smart, maybe even calculate it from first principles. Okay, so some very complicated calculations in condensed matter physics are about computing the electric susceptibility. And here we are talking about things that are not time dependent, right? We're putting a field, we're letting it relax, goes. There's the notion of a dynamical susceptibility, which is that you put an electrical field that vibrates with a certain frequency, and then the piece of matter will react differently depending on the frequency. But, you know, this is like for a much more advanced course. So the electric susceptibility is a characteristic of the piece of matter that we're considering, and we consider it as a given. And in that case, things become much more simple because you see, if I give you this number now, we can answer your question because you just compute D and you say, okay, it's linear isotropic. So I can just extract my E from my D by just reverse engineering this thing here, right? So so essentially, so in linear isotropic dielectrics, that's what you have, right? So this D is just epsilon 0 E plus P. And now I can just rewrite this, right, as epsilon 0 1 plus electric susceptibility times E. And by definition, this is going to be epsilon times E, where this this epsilon here is baptized the permittivity. Okay, it's just some number, and you'll find plenty of tables of these numbers for various pieces of matter. Yeah, so I mean, essentially, this is quite simple. Yeah. So this is just some nomenclature on this. So by all means, there's lots of interesting chunks of matter out there that are not linear isotropic dielectrics, but then things become much more complicated. So we're not going to consider them very much. We're going to focus on these things. Now, there's a bunch of examples that I invite you to look at, but I guess you already see that the transformation, the transposition of everything that we've done in vacuum or with even conductors to this setting is particularly simple, because now for linear isotropic dielectrics, we have, again, the same equations, just with different symbols in them. So we've got the displacement D instead of the electrical field E. We've got the permittivity epsilon instead of the epsilon 0 that we had. But for the rest, things are very much the same. So in particular, the application of Gauss's law, like we've done it, that works. One word of warning is that in general, the equation that we had for electrostatics, that the curl of E was 0, this is not going to be true for the displacement in general. For linear isotropic dielectrics, that's fine. But in general, for a complicated chunk of matter, the curl of the polarization is not 0. It doesn't have to be 0. It depends on your chunk of matter. So you can't use absolutely every single trick in the book, but at least for linear isotropic dielectrics, you can use really most of them. So we'll focus on those. Okay. So yeah, you'll have a few little fun things with this. Maybe just in the last minute, just to flash a thing that again you can refer to later. The derivation is quite simple, and we'll get back to general energy considerations when we do dynamics. But just for completeness here, I wrote the formula giving you the energy in a dielectric system. And the derivation is very simple. Let's just walk through it. What's the idea? Now we're reprogramming our brains to think in terms of free charge instead of total charge. So the free charge, rho f, is the thing that determines absolutely everything that occurs in your system. You bring in a certain amount of free charge, your system adapts to it. And, given the distribution of free charge, you can recover the displacement. And if you assume linear isotropic dielectric, also polarization and the electric field. However, now the question becomes how much energy is in there. And here you can again just engineer it from scratch, where you say, assume that I've already got a certain distribution of free charge rho f, and I now bring a little bit more in. So how much energy do I add to that? Well, the change in the energy is still just the amount of free charge that you put in times the potential where it sits. You remember these equations that we had for the energy, right? So the sum of the charges times the potential where they're sitting, that gives you the total energy. And here you're just massaging this equation by saying, indeed, my rho f is just the divergence of the displacement. So the change in rho f is the change in the divergence of the change in D. And now I just put that in the integral here. And you, as usual, assume that you're integrating over a volume that contains all regions where these potentials and fields are non-zero. So at the boundary of it, as you push that to infinity, the contributions vanish. So this first integral is just 0. And now you just get an expression for the change in energy, which is just the change in displacement dotted into the field. And now this is true for everything. But if you specialize to linear isotropic dielectrics, then D is proportional to E. So you just get this expression for the energy. It's very much like the the expression for the energy in electric fields in vacuum is just epsilon0/2 integral of E squared. And here you just have this change thing. So this is just like almost a side note, so that you can refer to it later. Okay. Any questions?